So let's get to the business end and try to explain. So remember that we want to do this genuine operator learning, and to do it we really need this, or at least we need some notion of discretization invariance, or let's say resolution invariance, whatever you call it. And to do it, we will use this concept of continuous discrete equivalence, that there is some equivalence between these two representations, between a continuous representation and possibly multiple discrete representations. Okay, so let's get started by just looking at some existing notions of continuous discrete equivalence. Where do they come from and how people have thought about this in other communities. So in fact, the starting point is, as I said, it's a detour into signal processing, because continuous discrete equivalence plays a big role in signal processing. So let me give you a 2-minute introduction to signal processing. I think many of you are already aware of this, so it's a very well known concept. And let me get so the question is very simple. Remember that my objective is to have a notion of continuous discrete equivalence for operators. But before that, let us start with the continuous discrete equivalence for a much simpler object, functions, right? So is there a discrete continuous equivalence for them? In other words, the question that sometimes is very important in signal processing is the following. Let us take a function which is L2, let's say intersection between continuous and L2 functions. Can this be uniquely recovered from point values? Now a function is a continuous object, a continuous quantity. Point values are discrete objects or discrete quantities. So the equivalence between them can be measured if one can be uniquely recovered from the other. Now in general, of course, this is not true, right? Means this picture that you see here is an counter example to that. So I have two functions, one in blue and the other is in green. So one has only one frequency, you can think of it, and the other has 10 or 5, whatever. And I'm just sampling at these points. As you can see, these are the red points on which I'm sampling. And clearly from just the point values, I cannot distinguish between the blue and the green function. So now you can see why this is an important question in signal processing, because in signal processing, at the end of the day, because you have to digital signal processing as it is called, you need discrete objects, and you have to deal, the ground truth is always continuous, a function. So this question was answered, at least in this setting, historically a long time back, by Whittaker, Kotelnikov independently, and eventually by Shannon, and it is called the Whittaker-Kotelnikov-Shannon sampling theorem. I didn't know that Whittaker and Kotelnikov also had some role to play. I always thought it was the Shannon sampling theorem. This is how most of us know it, as the Shannon sampling theorem. So what is the Shannon sampling theorem? It tells you that indeed there is an affirmative answer to this question, that a function can be uniquely recovered from its point values, but under certain caveats, under certain conditions. And what are these conditions? The conditions are, for instance, if your function, instead of being an arbitrary square integrable L2 function, it is belonging to what are called band limited functions. Now what is a band limited function? Band limited function again comes from signal processing, but it's simply when the Fourier transform, it's an L2 function, so you can always take its Fourier transform. And the Fourier transform is compactly supported. It is supported, this is one dimensional just for simplicity, it is supported between minus omega and omega. So the number of frequencies that the function has is limited, it's finite. So as long as the function is band limited, so that's the first condition. And the second condition is that your sampling rate, or let's say in numerical analysis jargon, your grid size, this has to satisfy a certain condition. The grid size here has to be less than 1 over 2 omega. This 1 over 2 omega is often called the Nyquist barrier, or Nyquist frequency, as some people call it. If these two things are true, then indeed the band limited function can be uniquely recovered from its values on a grid. Okay, so this is the Shannon sampling theorem. So we need a certain class of functions, certain assumption on functions, and at the same time we also need certain sampling frequencies, certain conditions on the discrete object. So this is where the equivalence is. And in fact, another way of rewriting the Shannon sampling theorem, or the Whittaker-Kotelnikov-Shannon sampling theorem, is in this representation here. So it turns out that because of these point values and band limited functions, now band limited functions are smooth, right, because then you can differentiate finitely many frequencies. So you can evaluate them, And what you do is that there is a unique representation here, a basis representation, and the basis elements here are given by the so-called sinc functions. So, sin x by x, right, the standard sinc functions. Some of them I draw some of them here, some of the examples of the sinc functions. So, what you do is that your continuous object, the function itself, the band limited function, is exactly equivalent. It's equivalent exactly to the following discrete representation, which is given in terms of the sinc functions and the point values on a properly sampled grid. So, this is the Shannon sampling theorem. In other words, if I make a projection onto this, let us say the span of this sinc basis, I recover the function back. So, in other words, this is the representation that you get. This is another retelling or a reformulation of the Shannon sampling theorem. We take a WKS sampling theorem. Okay? And if you do not have this, then what happens? In other words, if you do not have enough sampling frequency, or if you do not have these band limited functions, then you have a lack of the continuous discrete equivalence. So, here there is a complete continuous discrete equivalence. One is equivalent to the other. If you give me the point values, I can get the functions. If you give me the function, of course, I can get the point values. So, there is a two-way traffic. What if one of them is broken? In that case, you get errors, and these errors from harmonic analysis, signal processing, numerical analysis, these are called aliasing errors. So, they can be also, let us say, realized as projection errors in this particular case. So, it is simply f, the function itself, minus its projection. So, you can quantify them, for instance, in this case by the Poisson summation formula. So, remember, so for functions, in this very special case of band limited functions with sufficient sampling rate, continuous discrete equivalence can be formulated in this precise manner, and the lack of it leads to what is called as aliasing error. So, there is a notion already for functions where we can operate. Now, it turns out that this is a well known fact, all of us somehow know it from elementary numerical analysis, but there is a bigger generalization. This can be put in a very general perspective, and this is precisely what is done in harmonic analysis or in what is called frame theory. So, now this is a generalization of the, let us say, the signal processing concept of Shannon sampling theorem. So, what you do in this case is that instead of having a basis, so if you remember earlier we had a basis which was given by these sinc functions. Now, we can just generalize the notion of basis to that of a frame. So, a frame is a sort of a sequence or a set of objects, these phi's, they form a frame. So, this collection of objects in a particular Hilbert space, if these so-called frame inequalities are satisfied, as you can see that if A equal to B equal to 1, this is Parseval's identity, and you get back a basis. But frames allow for redundancy, they allow for something which is wider than a basis. So, you have both sided inequalities, and as you can see that because you have this inequality here, just from these frame coefficients, you can extract the function itself. So, this is the basic idea behind frames, and the link between the continuous and discrete when you have frames is provided by these objects called the synthesis operator and the analysis operator. The synthesis operator is very, very simple. It takes, for instance, these frame coefficients which are discrete, and it forms a function itself. So, from the frame coefficients you get back a function, that is the synthesis operator. If you do not want to deal with frames, just think of basis, right, and you get identically the same representation. And then the analysis operator is its adjoint, so it takes a function and it extracts discrete objects. So, this is from the discrete to the continuous, this is from the continuous to the discrete. And in general, if it is a basis, of course, they are related, they are the inverse of each other, but in general you can't say that. So, then you form what is called a frame operator, which is this TT star, and this itself is invertible. So, you can invert it, it's a positive operator, so you can invert it. And then we have another operator called the dagger or the pseudo inverse of the synthesis operator, which is also a link between the continuous and the discrete. So, essentially these are formalizations by which you can take a continuous object, a function, and you can read out its discrete counterparts, or you can take discrete objects and you can read out functions. So, it's a generalization of a basis, and at the end of the day you have this frame reconstruction formula, which is nothing but a generalization of this basis reconstruction formula, right. So, you have these coefficients, these discrete objects here, and of course, in general this is not the identity. So, you have to, let us say, account for that, and you can represent the function, and this is very, very general now, right? Because now we are allowing not just one particular basis or basis, we are writing everything in terms of these frames. So frames are a way to conceptualize or formulate continuous discrete equivalence for functions. And when you don't have this, so in particular, if you take a subspace of some what are called frame sequences, these are just a collection of objects, collection of members of the Hilbert space, and you take their closed span, and whatever, if you don't belong to here, if you don't have this continuous discrete equivalence, you get an aliasing error. Okay? So this is just a generalization of what I wrote for the Shannon sampling theorem. In other words, so what this provides us is, if your functions, there is an automatic manner in which continuous discrete equivalence can be expressed, and it is expressed in terms of these frame coefficients. And the important point here is, if you don't have it, then you will get what is called an aliasing error. So this is a very, very basic 5-minute introduction to, let's say, frame theory and continuous discrete equivalence for functions. By the way, just when do I suppose, then I'll pace myself accordingly. When am I supposed to stop? 20 past. So I have 1 hour 20 minutes. Are there any questions so far? So this is just for functions and basic signal processing and harmonic analysis. No? Everyone is okay with it? Because soon I am going to build on this. So if there are some questions, yes, please. I'm not a harmonic analyst, so I can only maybe there are some in the audience.
Hello, I'm not very clear about what are the conditions that could lead to a lack of CDE in this case. Because for sampling, if we do not respect the Shannon inequality, we don't have CDE.
Yeah.
And so with frame theory, what are the conditions?
So it's exactly the same. So there is, see the point, okay, that's a good question. Maybe I should have spent a little bit more time here. So you can see here that you take these basis elements, right? And then you project a function onto these basis elements. If it already lies in their span, then of course the projection error or the aliasing error is going to be 0. So you can represent this function entirely in terms of its basis elements. Okay, is this clear? So if you don't, then you make an error, and this is precisely the aliasing error. It's exactly the same here, except that it is done in terms of frames. So you take this sequence here, okay, you form a closed span of this sequence, and you do the projection. Okay, so if they belong to this closed span, that's why I this is the projection operator. If they belong to the closed span, nothing is to be done. Okay, if they don't belong to the closed span, then of course you have an error. So it's just a generalization of precisely what happens for basis, or in particular for the sinc basis for the Shannon sampling theorem.
Okay, but it means that we have no mean to know a priori if our function belongs to the span of the high.
Yes, or you either have to know it a priori, or you find out a posteriori if it is or not, if it has aliasing error, for instance, right?
Yes.
Then you compute the aliasing error, and then you see that it has. Okay?
Okay, thank you.
Okay, so this is it's good that you asked the question so that everyone is clear about what exactly is happening here. This is just an automatic way, a rigorous way, let's say, to formulate this concept of continuous discrete equivalence. By the way, wavelets are, I'm in France, so I have to talk a little bit about wavelets. Wavelets are classic examples of frames, or wavelets, class of wavelets, they form frames. One of them is the Mayer, Yves Mayer, how do you say it in French? Yves Mayer, his family of wavelets, one of them is that. Okay, so this is all for functions. So for functions, there is a well-defined way in which you can go from the discrete to the continuous, and you can come back to the discrete, and you can easily quantify what are the errors that are there. Now remember, our objective is not to deal with functions, right? Our objective is to deal with operators. So this is where it becomes a little bit more mathematical, and in fact, perhaps to our surprise, there was no proper concept. So this was introduced in this recent paper, not that long back, a couple of months back. And Roberto and Emmanuel are also co-authors in this paper, so several people. And the idea is to extend this concept to operators, because before dealing with operator learning, we first have to understand what is continuous discrete equivalence for operators themselves. So actually, these commutative diagrams play a very, very important role, and you'll see why. So remember, so my operator is a mapping. Now I'm Hilbert spaces. This can be done for Banach spaces, but this will be sort of mathematically tedious. So let's stick to Hilbert spaces, and they're large enough, interesting enough by themselves. So you have a mapping, an operator. I call it as U now because it has nothing to do with our operator learning, which had to do with the G. So you take a mapping which takes Hilbert space and it maps to another Hilbert space, right? So now remember that at the end of the day, I want to identify this with discrete objects, because that's how I am going to link the continuous and the discrete. One way to do so is by the following route. So I take these frame sequences, in general frames, but in particular you can take frame sequences. I call them as psi and phi. So psi is a frame sequence sitting in this Hilbert space here. Phi is a frame sequence in this Hilbert space here. And the whole point of frame sequences is that they allow me to take a function, a continuous representation of a function, and to sort of project it to a discrete representation and to go back. So now this is done by this synthesis operator and its inverse. So here this is a continuous object. I can pluck out the discrete object, which is right here, and then I can go back from this discrete object, discrete representation here, back to a continuous representation through my synthesis operator. So this is the way it operates, and then here is a discrete operator between two index sets. This could be finite dimensional. So this little u is a mapping. It's essentially a function, right? It's a glorified name for a function. It takes inputs in discrete operator, as we call it. It takes inputs, discrete inputs and discrete outputs. Here it is continuous inputs and continuous outputs. And what we want is this diagram to commute, right? Because then there would be some representation which is equivalent at both at the continuous and the discrete level. In fact, for any of these pairs, or not pairs but tuples, here 4 tuples here, you can define an aliasing error operator now. So it takes your continuous operator, your discrete operator, and it takes these frame sequences, and then you write what is the error in this diagram commuting. So this is precisely my concept of aliasing error. So this is just a generalization of what we had seen before. It's a mathematical formulation of that. And so in general, this could be non-zero, right? Means this is if you take a general operator, of course this is going to, and general frame sequence, this is going to be non-zero. Now the whole point is we want this to be 0, right? We want this to be 0 because we want equivalence between the continuous and the discrete. If not, then we have to estimate this aliasing error. But for the time being, let's want this to be 0. In that case, we call our, so this is a definition, we call the continuous operator and its discrete counterpart or discrete representation to be representation equivalent. This is just a name, representation equivalent, if this aliasing error is 0. And not only this is, of course, you can do it for one particular choice, but we want this to be 0 not just for one particular representation, but for any which satisfy these kind of range conditions. This is a bit mathematical to explain, but these are, let's say, some boundary conditions that we want to impose. So long story short, so what I want to do in this is that I want this diagram to commute. If this diagram commutes, then I have a continuous discrete equivalence. I can represent my continuous operator uniquely and stably in terms of my discrete operator here. So this is a thing that I can put on the computer. This is a thing that I can't put on the computer, but it does not really matter because I can always go between one and the other. Okay, so this is the basic sort of mathematical bulwark of what I'm trying to represent. And because there is a uniqueness of discrete representations, you can always flick. Remember that at the end of the day, you have to have multiplicity of discrete representations. This was the picture that I had. So you had multiplicity of discrete representations. We wanted to somehow patch them together. And the way to patch them together is through this particular change of variable formula or change of frame formula. So let's say that these are two different discrete representations out here, but they can correspond to the same continuous representation. Okay? So what you do is that you start here, you use the synthesis operator to go here, no, the other way around, you go here, and then you come back. So since this diagram is commuting, you can go whatever way you want. So both these discrete representations have the same underlying continuous representation, provided that the aliasing error is 0, and we have this continuous discrete equivalence. It looks a bit sort of abstract. I will give concrete examples in a bit, but you can appreciate that this is where it is coming from, right? We started with functions, we had a clear notion of continuous discrete equivalence there, and then we generalized that notion to operators. So this has nothing to do with machine learning, there's nothing to do with solutions of PDEs so far. It is purely at the level of function analysis, right? So this is where it is. So what we achieve through this representation is, or through this definition rather, representation equivalence, is that the discrete and continuous operators are equivalent to each other. So our multiple discrete operators are equivalent to the same continuous operator. Okay, is that point clear? Okay, so let me now, with this bulwark, with this sort of theoretical basis, we can sort of define what are called the sort of the core argument of this discrete and continuous equivalence in what are called as representation equivalent neural operators, or RENOs. Let me explain this a bit. So neural operators, just like neural networks, are particular objects which map finite dimensional spaces to finite dimensional spaces, and they are based on compositions of different quantities. That is what a neural network is, right? A neural operator is something which maps functions to functions, right? So this is sort of roughly speaking the definition, that it maps functions to functions. But now we remember that just mapping functions to functions was not enough, because we ended up into, where is the, oh, sorry. We ended up with all these problems that you saw. So you needed a little more tight or more constrained definition, and this is precisely provided by this definition of RENO, or representation equivalent neural operator. So what do? Again, everything is still layer wise. It's very much functional analysis. So what you do is that you have a continuous operator which is a composition of different layers. So just like as you would have in neural networks, you have its discrete versions which are also going to be compositions of different layers. And for each of these layers, you essentially have that the diagrams are going to commute. So each layer at the continuous level is going to map between two Hilbert spaces. Okay, so this is the first thing here. And because, and there is a sort of a synthesis and analysis operator, there is a frame sequence. So using this frame sequence, you define a discrete representation. So this is, if this diagram commutes, we know that there is no aliasing error, and we impose this at every layer. Okay, so each of these layers, the operator that you're going to design has to be structure preserving. It has to keep this continuous discrete equivalence. So this is the basic idea. The diagram has to be commuting. Now this is a very common practice in numerical analysis. We use it, for instance, in finite element exterior calculus, that which is based on this kind of commuting diagrams. We use it, for instance, in operator preconditioning, where one uses this kind of commuting diagrams. So it's the same kind of thinking here, right? So now what happens is that, so if you impose it, I'll give you of course concrete examples in a bit. So far this is abstract. So if you impose it at the level of each layers, then it is very almost trivial to prove that these compositions, so there is no aliasing error in each layer. Okay, so that's the whole point, that there is no aliasing error. You can operate between the continuous and the discrete. So of course when you compose all of them, 0 multiplied with 0 multiplied with 0 is always going to be 0. So you have no aliasing error for the whole operator. And if you did not have it, then in principle it could happen that you make a small error in the first step, but that gets multiplied with a larger error in the next step, and a larger error in the next step, and so on, and the aliasing error can be large, right? So this is an important point, that we don't want any aliasing error. We want it to be 0. So it allows us to have structure preserving discrete representations. There is these diagrams commute, and also very importantly we have a natural change of frame formula, which essentially goes back to this picture that I had before. And you'll see some concrete instantiation in a bit, but so essentially I can always change frames, because at the end of the day I am dealing with the same continuous objects. So even if I change the discrete objects, I can always move to another continuous object, and this is given by this formula here. We don't need to check it. This is the way to express it. So again, just trying to summarize, a neural operator which is representation equivalent for each layer has no aliasing error. So when you compose them together, then there is no aliasing error for the entire combination. Okay, and this is the definition of a representation equivalent neural operator. So I think Olga made the point before the break that at the end of the day, you have to deal with some sort of finite dimensional representation or some discrete representation. And this is the discrete representation that we are positing as a structure preserving form of it. So yes, please go ahead.
Thank you. So just a quick question.
Yeah, please.
Why do you need to introduce a frame? So far it seems that you can just get away with a finite dimensional basis.
We could use basis, but we keep it general, right? So for instance, if you use things like wavelets to design your operators, then you can't work with basis anymore.
Then the question becomes, when you have a frame, the representation is not unique. So
you don't need a unique representation.
But if you introduce errors, do you have any issue with
No.
errors that propagate?
No, this is the whole point, because there is no need for a unique if I understood your question correctly, let me just go back to this slide here. So as you can see that there is no unique representation, because then you have, you see, you can always go between this discrete operator to the continuous operator and then go back to this discrete operator, and you introduce no errors in this entire process. So composing these objects means that you don't introduce any errors. This is the whole point. Is that your question, or did I understand?
My point is that when you go from the representation, there's more than one representation that correspond to the same function. It's a frame. You have not or
if you change, okay, so your interpretation is what happens if we change the frames completely, or
no. You have frames. Normally they are overcomplete.
They are redundant, yes.
Redundant. So that basically means that there are more one representation that represent the same function.
Yes.
So my point is, like, if you make if you have stability issues, or do you have
no,
an error?
you don't actually. Okay. This is the whole point. Okay, you don't. If you are representing the same continuous object, you don't.
Even if the representation is not unique.
Even if the representation is not unique. This is the whole objective. Any further questions? Yes. But I could have simplified my life just by sticking to basis, of course. But I wanted to keep it as general as possible. Or we wanted to keep it as general as possible to allow for more possible redundancies. Yes?
So for these sequence spaces like I and K, or I prime K prime, are they compact, or like in the same way for like...
you mean are they finite or not?
They're finite or compact. Like are you taking a sequence space over I, which is a compact set, or...
It depends. Means you could take a finite, for instance, if you take band limited functions and so on, then of course they are, right?
Yeah.
So it depends. So it's more general than that.
Okay.
So this is a very, very general definition. It need not necessarily have that property.
Well,
but in practice, we need it.
Because I'm having trouble seeing where you have the compactness, like Olga mentioned.
It will come later.
Okay.
So it will come later. The compactness comes from the fact, for instance, that if you have band limited functions, you can represent them with finitely many points. That's where the compactness is going to come from. One example of this. You'll see in a bit. Okay, so shall we proceed now? So we have this theoretical abstract axiomatic framework. Essentially, we have some axioms. We say that it's a neural operator only, or a representation equivalent neural operator only if there are no aliasing errors, only if there is a continuous discrete equivalence. Then what happens? Do you have some examples of it, right? Means this is sort of the, why do you have a concept if you don't have examples? Okay, so we'll do several examples of it, and this is how I will try to give you also some context here about different neural operators or operator approximation methods. The first ones are, of course, CNNs. So if you remember, so maybe I go back a little. So we started out with this example with CNNs and interpolation, and essentially we wanted to explain or exclude this kind of behavior, right? And it turns out it's fairly easy, although it was not done before, that one can prove essentially that CNNs are not Renos in the sense that they are not representation equivalent, because the way it is, and I don't want to give too much of detail, I just want to explain it visually. So what CNNs do is that these are discrete convolutions with a fixed kernel. So this is sort of the idea behind CNNs. So you have a signal which is given here. I drew the signal here. You are going to sample it at points. This is just one dimensional. and then you have a kernel which is represented here, and you sweep the kernel in order to compute the output of the CNN. So this is just the convolutional layer in a CNN. There are also pooling layers and let's say activation layers and so on. But remember that our definition is a layer wise one. If you don't have it in every layer, then it can't be, you might have errors that propagate. So now, of course, you change your sampling. So when you sweep the kernel, you get some answers. For instance, you take this kernel, you multiply, do this operation, then you get some answer. Now let me refine the grid. I could also coarsen it, but for simplicity, I refine the grid. So when I refine the grid, then of course these point values get changed, because now these point values are no longer the same. These 3, so it's a kernel of size 3. So when I sweep, I'll get a very different answer. I'm not resizing the kernel, it's exactly the same. So of course, when you do this operation, and you look at the change of frame formula, one can prove rigorously that it is not the same. Okay? In other words, since you don't resize your kernel, you keep the same kernel. When you resize your input, you don't do anything, but you get errors. And this properly explains what we saw before, which was this picture here. Okay? So this is a rigorous explanation of why we saw this picture. So CNNs are certainly not Renos. But can we develop Renos? You know, are there any which have this continuous discrete equivalence? And one way to think about it, and I know that people who developed these methods did not think like it, right? So this is a reinterpretation of some well-known methods, is what happens to numerical methods, right? Whether we have finite differences, finite elements, spectral methods, and so on. How are these methods doing on this score? So if you look at traditional numerical methods, one way to interpret them is through the following picture. Because at the end of the day, these are also operator approximators, right? So one way to interpret them is, so you have an operator now, which takes a space x to a space y. This could be Banach spaces. One way to think of them is that I take an encoding. So I take an infinite dimensional object and put it into finite dimensions. For instance, for finite differences, this would be just point values. I take my initial data, for instance, and I sample it in point values. For finite elements, this could be, for instance, node values. Finite volume, this would be cell averages and so on. So you have an encoding into finite dimensions. Finite dimensions depends on your grid size or the number of finite element functions that you have. Then you process them. For instance, you could use the physics here, the PDE. This is typically the scheme. Or if you have, for instance, a matrix inversion like in finite elements. So this is what is done there. And you get a discrete set of values, which is reconstructed or lifted to infinite dimensions, for instance, by different kinds of interpolation. So for finite differences, you have polynomial interpolation. Finite elements, you have the usual Galerkin type interpolation. For spectral methods, you have Fourier interpolation and so on. So essentially, you can reinterpret any numerical method as take something infinite dimensional, get something finite dimensional out of it, process the finite dimensional, and use some basis in order to go back to infinite dimensions. So this is one way of thinking about practically any numerical method. It turns out that this can be used to construct neural operators, potentially representation equivalent neural operators. And one way of thinking about it, so everyone agrees that this is a scheme by which you can reinterpret practically any numerical method. And one way to think about it is, okay, so if you have, so these are, one can call them as spectral neural operators, but I'll give you some context here. So for instance, there's a lot in this slide, so I'll walk through it gently. So for instance, if you take a spectral neural operator and SNO, just like you do with a numerical method, I am going to extract some finite dimensional inputs. For instance, let's fix my basis as, or let's put it in terms of frames in the most general case. So I have some frames. I extract frame coefficients. So that is my finite dimensional encoding. I process the frame coefficients. So I take, for instance, a deep neural network. This is a finite dimensional object. So I can take a deep neural network. And in order to get back to the infinite dimensional setting, I can use my frame functions. Or in other words, you can think of basis coefficients and basis functions. So a particular realization of it was done in this paper from last year, where they used a Fourier or a Chebyshev basis. So what do? You start with a function, you extract its Fourier coefficients, you process the Fourier coefficients with a neural network, you get some answer, and go back to the infinite dimensional space by using the Fourier basis, right? So this is one way. So you replace the scheme here, the physics, by just using data, and the data is going to train this neural network. So now this is an example for a representation equivalent neural operator. As you can see, this diagram is commuting, provided that certain conditions are laid down. So in particular, our function spaces have to be periodic band limited functions, so that the Fourier basis has this nice properties. And then, as you can see, so what you do is, okay, there are some identity mappings here that you shouldn't care about. You start with this, you extract, you get a sort of of course, complex valued because there's a Fourier basis, and then you use neural networks here, and you go back using the Fourier basis. And at a discrete level, you're always working with complex valued sequences in some sense, right? So this is an example of it's called spectral neural operator, that you always work with a discrete representation. So extract a discrete representation, basis coefficients, process the basis coefficients, and then reconstruct, lift using basis functions later on. A generalization of this, even though historically this is not how these things came about, but this is a, let's say, modern in machine learning means a year later interpretation of this is provided by what is very, very popular these days, deep nets. They go back, the shallow version of them goes back to Chen and Chen in 1995, and then George Kaniadakis from Brown University and his group, they developed this notion of deep nets, and it's exactly in this setting with a little bit of a catch. So again, the extraction, so remember that there is an encoding. You have an infinite dimensional object, I need to go back to finite dimensions. So this is done, for instance, in deep nets. So here it is done by using Fourier basis, right? But here this is done just by using point values, point evaluations. So this is, you take the function and you evaluate the function at the points. I don't know how well you see, I don't see it at all, but these are just point values. And then these point values are processed and they give you this, let's say, basis representation. But unlike in the Fourier case, where the basis itself was a Fourier basis, here the idea is that you don't know what is the basis. Maybe for different problems, different bases are better. Like if you have a very unstructured grid, it doesn't make any sense to look at a Fourier basis. The idea behind this is that you also learn the basis, or in general the frame. Okay? So there are two neural networks. One is a neural network that takes the, let's say, the point values which are extracted initially, and then it extracts essentially basis coefficients, and another is a neural network that provides you with the basis. So as you can see, this is a slight generalization, because earlier we had, this was just a frame function, so the basis functions, but even now this is going to be a deep neural network. So you have two sets of neural networks, and they come together to form what is called a deep net. So as you can see, this is the representation. This is a neural network which acts on the output space. So it's a finite dimensional mapping. This is a neural network which acts on the input space called the branch net, which is also a finite dimensional mapping. And this you are going to learn in more detail, because in the exercise session today, you are going to learn how to code it essentially from scratch, right? Yeah. Or more or less from scratch. So we have prepared the code so that you learn how to do this. So, but you see that how this comes about, that there is a very natural way in which you can go from a fixed basis to a learned basis. But this is what the idea is, that there is a learned basis. There is a learned basis. There is a generalization or a variant of it, which is called the PCA net, where instead of using point-wise evaluations, so sensor evaluations are point-wise evaluations, instead of using point-wise evaluations, you use PCA. So you can always do PCA on data, and then you use a DNN, and on the output side you also do a PCA, but it's called a PCA net, which was developed by some people in Caltech. But the idea is the same, that you extract finite dimensional objects, you process them, and then you have a learned basis. So essentially this is the basic idea. So are there any questions about DeepONet? Because this is an important architecture, and we will do its properties in a bit, but if there are some questions, I'm happy to answer them now. Anyway, I needed some hydration, so no questions? Everything is okay? Okay, so now by doing this sort of, you're following the chat also, right? So there are no questions there. Okay. Okay. Okay, I see. Okay, so there is a. Okay. I see. I got it. I didn't see the Q&A. So now, by doing this, are we going to get represent? Okay, this is clearly a neural operator because it takes a function and it outputs a function. But the question is it a representation equivalent neural operator? The answer is yes, provided that certain conditions are satisfied. Always there are some caveats in this business. The first is, of course, since we are taking sort of point-wise values, you have to stick to band-limited functions, because then with the sinc basis, we know that there is this continuous discrete equivalence. So you take band-limited functions, and then since you are extracting the basis coefficients, because it's a reproducible kernel Hilbert space, are precisely point values. So since you're working with these point values, this is okay. And then the output space, because it's a learned basis, it need not even be a basis. It's just a learned frame sequence. This could be, for instance, this is just a span of these things. So as long as your mapping is a mapping between these two spaces, then it is representation equivalent. So coming back to your question about the uniqueness of the representations and why we needed frame sequences, this is a good example. Because here we don't know if this is a basis at all, because it has not been trained to be a basis, but it's always a frame sequence. So any finite set is a frame sequence. So at best, if you change it, then who knows what happens. Within these caveats, it is going to be a Reno, but if you break it, then it fails to be a Reno. So this is, for instance, many people say, oh, it's very good with depot nets because you can do random sampling. But random sampling is going to lead to, because the sinc basis and the Shannon sampling theorem is with uniform sampling. If you take random sampling, then you get aliasing errors. And this was already noticed in this paper, although we did not put it in this particular framework. And at the end of it, you just have the closed span of this space here. This need not have anything to do with, for instance, band-limited functions. Means the trunk nets that you learn, these need not be anything close to a basis. In fact, they don't look anything close to a basis. One can easily plot them. So there could be, they are representation equivalent in their closed span, but they may not be representation equivalent in any reasonable sense, because you are not enforcing that they are going to be basis. So there are these caveats. Based on these caveats, this approach indeed has some of these representation equivalence properties. In addition to that, it has some nice desirable theoretical properties, and this is some of the questions were also about that. So I'll spend a couple of minutes on that. So in this paper, we answered many of these theoretical questions, even though the setup of this representation equivalent neural operator was not there. The first question is universal approximation. So remember that we had this argument that neural networks are universal approximators. They approximate any continuous function, for instance, or any measurable function. It turns out the depot nets also have the same property, independent of this representation equivalence, that as long as you have, for instance, a mapping between Sobolev spaces, and if you take a measure, which is a probability measure on L2, with respect to this, if you have measurability, then there exists a depot net or a O net in general, because this can also be a shallow one, which has the arbitrary accuracy. So as much of accuracy as you want, you'll see in a minute how this error is measured. Okay, so this is the first thing. You have the same sort of universal approximation for operators that neural networks have for functions. So this is some version of it was already there in Chen and Chen quite a time back. But of course, universal approximation, as I have argued, is not enough. Things can have a curse of dimensionality and so on. And it turns out that you can do quite a bit of quantitative work. I don't want to give the details here, but essentially two things become very important. First is, because you are in this sort of infinite dimensional setting, you have a measure, which is the input measure on your input space or measure on your input space, and you have its push forward. This is what the operator does. So the covariance operator of these objects, this becomes very, very important. And eventually the bounds can be tracked to the spectrum of this covariance operator. It's a little bit like what you might see for reduced basis methods. And the second point is that the size of this object, it grows in the following manner. So to get an error of epsilon, the size of the depot net, there are different ways to measure it, but let's put them in the same bucket. The size of a depot net grows in the following manner. So it's 1 over epsilon as usual. This k here is some form of smoothness, because you are projecting it into finite dimensions, so you can measure smoothness. So more smoother your operator, somehow the more smoother things it acts on, easier to approximate. And this m epsilon here, this depends on the number of sensors, or the number of points at which you are sensing the function. So of course, to sense a function which is genuinely, or operator which is genuinely infinite dimensional, as epsilon goes to 0, this guy goes to 0, 1 over epsilon goes to infinity. So as you can see, 1 over, this goes to infinity, sorry, this goes to infinity, 1 over epsilon goes to infinity. So you have these two quantities going to infinity, which are exponentials. So of course, this is a curse of dimensionality. So even if just from approximation theory, you can see that because you are trying to approximate an operator, the infinite dimensional nature somehow becomes important in that sense. So a lot of the work in this paper was to argue why this is not a problem, because in general, yes, this is a huge problem, right? But because we are solving PDEs, the same sort of story again and again, PDEs have much more structure, and the structure is such that you can leverage it and you can get rid of this curse of dimensionality for different kinds of PDEs. So here's a whole library of PDEs that I looked down. There is elliptic, parabolic, nonlinear parabolic, Navier-Stokes, conservation laws, and so on. All these PDEs, what you do is that you leverage the structure and you show that the size of the depot net, which is given by m, only grows polynomially and not exponentially. Means this is the spatial dimension. It's not the infinite dimension that you're looking for. So of course, there is quite a bit of theory on that. So a priori, it seems that, at least from an approximation theory perspective, that indeed these things can do what neural networks did in the parametric case, right? This is exactly some sort of an analog of that. And you can also estimate things like the generalization error. After that, I can take some questions here. You can also estimate what some people call it as estimation errors or finite sample size. At the end of the day, you are plucking things out from a measure, right? So you want to see how many samples do you need. So here is an example of this error, which is, you can think of it as generalization error or a quadrature error. And then we also proved that in this case, the number of samples, the sample complexity grows like a square root. Okay, so even though it is in infinite dimensions, that does not really matter. So whether you are in infinite dimensions or finite dimensions, it always grows like a number of samples. But each of these samples is a PDE solve. So you are not in a, and from a infinite dimensional measure, you can only draw using random sampling. You can hardly draw, you can't do sort of quasi Monte Carlo or something like that, unless and until you have a parametric representation. So there will be some sort of a data issue here. So the bottom line here is that somehow these theorems say in some sense that depot nets should in principle work quite well, and there are hundreds of papers where these things are experimentally verified. Okay, is there any question about the very short introduction that I gave to the theory? So theory, you should have the mnemonic that whatever can be done for deep neural networks at finite dimensions can be done by O-nets theoretically in infinite dimensions. This is sort of roughly the mental picture. No? Yes? Time to catch up on some drink.
Good morning. I was wondering, I mean, what you mean exactly in these statements. I mean, for instance, let's take the Navier-Stokes equations, where actually we don't even know the existence of a solution.
No. This is
so I suppose you're postulating some a priori regularity on the solution, or perhaps capital T small enough. I don't know.
No. You are absolutely right, because you are postulating that the solution is in some suitable Sobolev space.
Okay, so this isn't like an a priori assumption.
Yes, absolutely. Okay. Which is verified in 2D, for instance, right?
Sure, but the word is not 2D.
Yeah, but as I said, means this is an informal theorem. This is
are there any results actually still on the Navier-Stokes where the dependency on the Reynolds number is somehow taken into account in these constants?
Yes, actually it is taken into account, and it has the same sort of dependence on the Reynolds number that, for instance, a spectral method has or a finite element method has. So it blows up as the Reynolds number goes to infinity.
Okay. Yeah.
So this is you're not doing any magic here. So
Thank you very much.
This is not the point. Yeah.
I have another question.
Yeah.
If you come back to your scheme with the other one.
No, somehow it doesn't do well with this.
Yeah.
No? Oh. Yeah.
Yes. So somehow you seem to make every time you fix a specific choice for your encoder and your representation operator.
Reconstruction.
And then you draw a kind of a theory out of this.
Yeah.
But in the beginning, somehow we were thinking about representations that are kind of invariant.
Yeah.
But if we fix this kind of choice, then we are going to lose our robustness against this kind of... you see what I mean? I'm just wondering if we can discover automatically these operators without having to fix them a priori?
This is a very good and difficult question, I would say. See, this is some existing architecture, right? So this is not something I invented. I mean, this has been around for quite a while. And there are choices that have been made. So for instance, it does discover this R here, because this R in this particular case is given by this learned basis, and it does discover that. So this is the idea. And the way this approximation theory works is by, for instance, you know that the Fourier basis is optimal for some particular problem, and then you can learn the Fourier basis using this learned basis. So this is a typical example of a proof. So some parts of it are going to be learned, but some choices have to be made, because at the end of the day, you need to make some particular choices. Otherwise, something has to be fixed, right? Otherwise, there's just too much of freedom in the design space that I learn. I probably at the end of my lectures, I have some discussion at least about how, for instance, encoders and reconstructors can also be learned. Here, for instance, R is a learned object, right? So this is this is sort of the secret, or not the secret, but one of the issues with this particular architecture.
Thank you.
Okay. Yes, please. You can shout.
Okay, so the next slide where there are all this complexity.
Yeah.
Yes. Is it correct that I can try to compare this epsilon to some delta x? I try to compare this slide command with the classical solvers, PD solvers. Then epsilon is kind of like a delta x or delta x to some power.
Yeah.
So then what's going on if I compare these?
That's a very, very good question. If you compare them, you'll get identically the same answer, because
okay.
So in this particular case, at least these last two, it has been proved precisely by last three actually. It has been proved in this paper we could do this in another manner, but these two, for instance, is done precisely by a finite difference method or a finite element method that is emulated. So you'll have exactly the same rate. But the first two you use analyticity or holomorphy. Because you use holomorphy, then of course, but they are holomorphic, so you can't. That's why
it's good, but in practice,
in practice, the constants are bad. I agree with you. But these are not.
Okay, but we can compare. This is information.
We can compare.
And they are roughly the same order.
They are the same order, actually, not roughly.
Thank you.
But this is approximation error. This doesn't tell me anything about the usual caveats, right? So I want to make. But it's a good question that there is indeed this comparison. Okay, so what's the issue then? Means everything seems to work, right? Let me see. Okay. So one of the issues, maybe some of you might have already guessed it, is at the end of the day, we are doing some sort of a linear reconstruction at the end with a basis and so on. So you could leverage that to prove lower bounds. There are some explicit lower bounds. And in particular, this tells you that this is the same as in reduced basis methods, means as long as the eigenvalues of this covariance operator decay fast, the error can be rather small. But what happens when they decay slowly? For instance, when you have transport dominated problems, then you end up in trouble, because in principle, this error can go very, very slowly. For instance, it only decays linearly or sublinearly, with the number of eigenvalues. Then you need large system sizes to represent your solution, and then you need lots of data to feed it. Things like that, right? And actually, one would think, okay, who cares, right? This is what the theory says. Maybe this lower bound is not respected in practice, but actually it is, because this is an example. So you just take the Burgers equation. So Burgers equation for me is the viscous Burgers equation, not the, I'm a conservation laws person. So it's ut plus u square over 2x equal to 0, and u at x0 is u naught of x. You can take whatever boundary conditions, let's say periodic boundary conditions on the unit interval. Now what I do is I take this equation, I give it data, which is an infinite dimensional object, let's say a Gaussian random field with some sort of let's say correlation length, and at the end of the day this is what the solution looks like at some time. You can see that there are shocks at different places. There is a weak shock here, but these will eventually merge and so on. So the orange is the ground truth. I trained the DeepONet on this. Remember that I had some approximation error, but you see at the end of the day I am completely off. The shocks are completely off. The structure is roughly captured, but the details are not captured. So you get 30% error. So this shows that this is completely unacceptable. So for transport dominated problems, you might have some trouble. So there are problems, and in fact you will see several examples, probably the speed at which I am going after the break, after the lunch break, but you will see several examples of that. In practice, this is not such a good architecture, because in principle it's a good architecture, but in practice it is not such a good architecture. So we need alternatives, and there have been alternatives around. And one class of alternatives that I will spend a bit of time on, which are very popular these days, they were formalized in this particular paper from some people in Caltech, but they have a longer history. Let's say around 2020, 2021, these things were proposed. They are some form of neural operators, and the idea in this is very, very simple. There are different ways to come there. One idea is that you remember that neural networks, for me, are simply this kind of parametric compositional maps. They are compositions of elementary functions, and the elementary functions are this, let's say, affine functions. So you have a matrix vector multiply, and you add a vector, right? So, and then you have this pointwise nonlinearity. So here, of course, the input is finite dimensions, and the output is also finite dimensions. Now, suppose we do this thought experiment. We can't do it on a computer. We have to discretize. But let's do this thought experiment that my input and output are going to be functions, and I can somehow compute with these functions without having to discretize them. So the idea behind what these people proposed is, let's generalize this to infinite dimensions. So what do you do? So what do I have to generalize? I have to keep compositions as before. The compositional structure should be very much there, but then I change my sort of inputs to the network now, because I have functions as inputs and functions as outputs. So at a given hidden layer, my input is going to be the function v. So as you can see, v, this is fed to the NL hidden layer, and then something happens. So instead of having a vector, it is very natural that I have a function, right? I am taking a function as the input, so my bias will also be a function. So this is a straightforward generalization of that. But now how do I generalize a matrix vector multiply, right? So how is a matrix vector multiply generalized to infinite dimensions? Now, from elementary function analysis, we know that the simplest way to generalize a matrix vector multiply is to do a kernel integral operator, right? It's a kernel integral operator, and this is precisely what is done. So instead of having a matrix multiplying a vector, I take a function, I multiply it with a kernel, and I integrate across the kernel. Okay, so this is one particular way in which you can realize matrix vector multiplies. So this is now an infinite dimensional analog. By the way, for instance, if you think of the Green's function, we want to solve the Laplace's equation. The Green's function precisely gives you formulas like this, right? So this is another motivation, but in general, it's a generalization of the matrix vector multiply in finite dimensions. So this is what it is, and this is a generalization of the Weiss vector. And then for the nonlinearity, let's just apply it pointwise. So in function analysis, these are called Nemetsky operators. So the action of the operator on a function is to evaluate the function pointwise. So this is the sort of general scheme of these class of neural operators. And as you can see, without bothering about discretization, we just take functions, we operate on them, and then we get functions out. Take functions, operate on them, and get functions out. Now, of course, there is an issue, because so how do you choose the kernel? The kernel is what is going to be learnable, right? So learning parameters are in the kernel, just like the weights and biases. Now these are represented in this kernel and in this bias function now, and different choices lead to different kinds of architectures. But at the end of the day, we have to discretize. Means we cannot put these formulas into a computer. So we have to discretize, which means that I have to compute this integral. Now you can imagine that now my complexity here is going to be quadratic with respect to the number of points. So if I take n points in space, this complexity is going to be quadratic because I am doing this multiplication here. So just imagine in 3 dimensions, this will be a very, very large computational cost, because I take points in 3 dimensions, my kernel is 6 dimensional, and then I do this, let's say, kernel function multiply. So this is not going to work. We need some smart version of this algorithm, and this was provided very soon after the initial papers by the same group. They are based in Caltech, and this is one of the arguably the most popular operator learning architecture that is around today. I think it's called Fourier neural operators. It has more than 1,000 citations already in like 1.5 years, 2 years. So it was proposed in this paper by this group in Caltech, and the idea behind it is the following: that remember that this kernel here is what makes my computations expensive. So what if I make it translation invariant? It's a very nice feature, translation invariance. So if I have a translation invariant function and I multiply it with another function and I integrate, then essentially I have a convolution which I can represent ideally in Fourier space, right? Particularly if you are in Fourier space, I can represent it in this particular manner. So what do I do in order to do the calculation here is I take a function, I take its Fourier transform, and then the kernel is now just a Fourier multiplier. So this is a Fourier multiplier, and then to go back to space, I took an inverse Fourier transform. So now, assuming that everything is continuous, this is a very, very nice operation, right? So what does a FNO do? Remember that it has all these layers. Again, FNO is an architecture that you are going to code essentially from scratch in the exercises today. So pay attention now about how this is going. So you take an input. This is an input function. Let's say the coefficient of a PDE, and this is going to be my solution, right? So what does the FNO do? Is it takes it. It has what is called a projection or a lifting operator, because all the time in machine learning, you believe that there are some effective coordinates or latent variables where you want to project or lift your functions. So this is just a linear operator, a linear layer, matrix multiply, which projects it onto or lifts it onto a larger dimensional space. And then each of these Fourier layers, they have the following, let's say, functionality. You take a function, take its Fourier transform, use a Fourier multiplier, which is learnable, inverse Fourier transform back into space, and you keep what is called a residual connection. So that would be like a identity plus compact, a Fredholm type operator, if you want to think of it. So here, for instance, I would have added a matrix, point-wise matrix multiply. So that would be like a identity plus compact operator, Fredholm operator. So this is what is called a skip connection. So this is in physical space, this is in Fourier space. You combine them and you keep on doing this again and again till you project back into where you are. Okay? So at the continuous level, it's very, very neat, very, very nice to write down. Everything can be done analytically somehow. But of course, on a computer, I need to discretize it, right? And in order to discretize it, then as long as I have sort of a Cartesian domain, Fourier transform, DFT is very fast, because you can always do this with FFT. And this is what is done. So because instead of having a quadratic cost, which would be the case if I just use this formulation, with FFT, I can go log linear. Right? So this is always the advantage of working in a, let's say, periodic or a quasi-periodic setting, that I can use the FFT. So what do I do now? I take a function, sample it on a grid. This is important, otherwise how else will I use my DFT or FFT? Then use the FFT to compute the Fourier transform. This is log linear. Do a Fourier multiplier here. This is learnable, and this is also done now. Instead of having all the modes, you project them into some finitely many modes. And then again do an inverse Fourier transform, inverse FFT very fast, and then you combine them and you do these layers. Okay, so this is sort of the architecture. It's a It's a very natural architecture in some sense, even though sort of it was presented in a complicated manner, but there is a very natural way to present it. Are there some questions on this architecture now? Means you are going to implement it, bulk of you, not everyone, but bulk of you are going to implement it later today. So, no? Everyone understands it? We'll find out, right? This is something we will verify at the end of the day. Okay, so this is an architecture, and this is somehow the difference now from what I did before is a subtle one. The subtle one is, in this case, you do a sort of a, you don't extract in principle, in practice you'll do it, but you don't extract a basis and then just act on the basis coefficients. You sort of do end-to-end in a sort of machine learning manner. This is roughly the idea. And actually, does this work? Means in the beginning, means there was some doubt, right? Means they have numerical experiments, but everything is done in Fourier space. So can you really represent all functions that way? So soon after the paper came out, we came out with the universal approximation theorem, which is out there. It says it has exactly the same sort of approximation properties. Any measurable operator, just like DePonet was universal, this is also going to be universal. Almost any reasonable thing is universal, so that's not a big thing. And remember this curse of dimensionality, this exactly the same way. So this was coming back to Bruno's question somehow. Okay, let's go here. So exactly similar kind of theorems can be proved also for FNO. And in this case, the rates are exactly that of spectral methods, because we somehow condition it on spectral methods, and so nothing is some numerical analysis, but it's not anyone can do it kind of numerical analysis. The universal approximation theorem was not standard numerical analysis. This required quite a bit of work. So it has exactly the same approximation properties as DePonet. Then why should I use it, right? Why should I use it compared to DePonet? And this is the both theory and numerics that I'm rather proud of. So what we did in this paper is the following. That remember this, for instance, Burgers equation or even linear advection equation. It's a very simple problem. You have linear advection equation. You have jump discontinuities, and you just move them, right? This linear advection equation. You just move them. It turns out that to obtain an epsilon error, with the DePonet, you can prove, because there is a lower bound, in principle, that the cost is going to be quadratic in the error. So it's going to be quadratic in the error, which is what it is. But for FNO, you can prove that it is not just going to be, let alone quadratic, it's not even linear. It's actually log. So it's a very compressed representation. And this is not standard numerical analysis, because standard numerical analysis will precisely give you the quadratic cost. So this is non-standard numerical analysis. It was hard to prove it. It uses special properties of transport equation and of Burgers equation. You have a similar result for Burgers equation, and you see that in practice, that the errors for this particular case, there are some Resnets and so on as a baseline, but compared to DePonet, you have 10 times better error. So you have the error reduces by a factor of 10. So there are cases where this is even provably better, let alone empirically better, which is the case in many, many cases, but it is even going to be provably better. So then what is the catch then? So then I should finish now and say that this is the best model and let's all go and swim. But we still can't do it. So because are they Renos? Now remember, all the time I had this representation equivalence. So is this, so far I didn't touch it for FNOs, right? I showed it for DePonets, but I didn't touch it for FNOs. Now let us try to understand this a little bit, because this is an interesting story in itself. So first of all, so remember the definition of Renos is this discrete continuous equivalence, this kind of commutative diagrams for every layer. So FNO has this Fourier layer. So it has this sort of convolution is done in Fourier space, and it has a nonlinear activation function, a pointwise nonlinear activation function. It turns out that it required a little bit of work to prove that actually by doing this convolution in Fourier space, you can prove that that layer is a Reno. And the way you do it is because you're always taking a function, you're computing its Fourier transform, but you're projecting onto a fixed number of modes. So you change the grid, You can take a grid and you have a finer function, but you still are going to project it into the same sort of number of Fourier modes. There is a proof which says that, yeah, indeed, this convolution in Fourier space indeed is able to keep this representation equivalence. But that's not enough, because we also have nonlinearities. And this can change things. And let me explain it. So this is with respect to periodic band limited functions, means it's not in arbitrary places, but things for which there is a Dirichlet sort of basis. So now what about these nonlinearities? Now nonlinearities, they break these band limits. I'll give you an example here. So if you look at this function here, so the signal is in orange. So you have this function here. It has actually the frequency is between -20 and 20. I don't know how well you see it. But now I apply ReLU, for instance, in purple, on magenta, then you can see that the negative parts are completely cut off and the positive parts remain what they are. And then when you just trivially, when you compute its Fourier transform, you can see that it has gone out of the band limits. You can clearly see that. So whenever you take a nonlinearity, you break the band limit. This is also true for another activation function, JLU. It has the same kind of representation. So in general, you cannot guarantee, and the simplest example is you take a function, let's say sum of 20 signs, take its square. You know, now when you take its square, there's a nonlinearity, you'll get 40 signs. You can't get 20 signs anymore. So this is the nonlinearity is the break band limits. So even if convolution keeps your band limits and keeps representation equivalence, nonlinearities could break them. Maybe they don't, but in general they could break them. So this means that they are not necessarily Renos. So there is an issue with them. They are not necessarily Renos. And so the whole objective that we started out with somehow breaks down here, right? Means this is the point. Are there any questions, or did people understand this? Or okay, let's see an example just to clarify that. This example that was constructed by Emmanuel, and it's an interesting example because it's an extreme example. So what we do with the operator now, it has nothing to do with solutions of PDEs. It's an operator that takes inputs on a grid, so on a space of band limited functions, periodic band limited functions, and then it's essentially random inputs and random outputs, but these are well defined, means it's a completely valid bona fide operator. But then you can see that with FNO, for instance, when you change the grid, this is when, so remember the representation equivalence is when I change the grid, I should not get an aliasing error. So if you, for instance, make a finer grid or a coarser grid, in both cases with FNO and CNN, you see that the error goes up. They are not representation equivalent. SNO, on the other hand, as long as the Nyquist barrier is maintained, is preserved, so that is if the grid is refined, so you have enough resolution to sample these functions, you see that the error is completely zero. As long as you break that, you break the Nyquist barrier, which means that you cannot represent the function, it's not a frame sequence anymore, then of course the error goes up. So it is in theory and in practice, it is not a Reno, whereas at least under certain conditions, SNO is going to be a Reno. And this is not just a theoretical problem, because on the same problem that we had before, why doesn't this work? Yeah. The same problem that we had before, where we saw that the CNN, the error was changing with mesh resolution. For FNO, it does exactly the same. Much less pronounced, but it is there. So at 64 squared resolution, it has an error of 4%. We can argue is 4% good enough, but it has 4%. But when I change to 128, this goes up to 6% with 5.5%. With the CNN, it was 20%, right? So it has gone down, but it's still there. And here it goes up to 6%. So it is also not a representation equivalent neural operator. So it does not help to, we have all these fancy things, but because of the presence of nonlinearities, you get out, you don't have this sort of invariant representation. Okay, so this was sort of one of the key points, and this is very recent. Means these papers are a couple of months old. Not FNO. This is 2 years old. But these properties they have been known for a bit, but they are formalized now. So any questions on this particular aspect? People are getting hungry, I think. But we have 15 more minutes, right? Or Okay, so I think so the point is, or you tell me, means, okay, so I wait for the organizers to, so do I have any instructions for me or no? Okay, so now the idea is, can we combine these aspects? If you remember, so DeepONet or SNO, for instance, they had this sort of Reno aspects, but they were not expressive enough in some sense. FNO was somehow very expressive, but when you change the grid resolution, that property broke down. So could you design an expressive Reno? And our starting, I will show you that, means, there is no suspense. But you will implement FNO later on, so you'll see for yourself how it does. So what we do here, there is a question, by the way, no? It went from 1 to 2? I'm also tired, means it's sort of. Yeah, what is the question?
So there are questions. So the DeepONet does not match the Siddhartha, right? Since it's not resolution invariant.
Well, it is resolution invariant under some conditions. So I think I presented the conditions very clearly. Also, FNO is also resolution invariant or representation invariant if the nonlinearity maps onto the right spaces. So we have a set of conditions, and I think in one of my slides I had a very clear. No, I remember. Yeah. So if so, there's a clear answer to that.
So the second question, for these FNO results, did you truncate the number of modes?
You have to. Means, so you have to truncate the number of modes because again it's a question of finite approximation. So now don't ask me the exact number for this particular numerical experiment, but the architecture itself, this R has support in a band. Okay, so this R, the Fourier multiplier, has support in a band because you are not going to write 100 and 1024 frequencies, right? Means you have to, the computation is going to be very, very expensive. How many modes have been used here? 16. So, 16. Those are the questions.
Is it okay? Yeah, those are the online questions.
Okay, good. So now, so the desire to have expressive Reno, the way we are going to go about it is to use convolutions actually. Means, so convolutions, remember I sort of criticized convolutions quite a lot before, but now somehow can they be brought back into the reckoning, right? Because what are the advantages of convolution? So convolutions have a long history in machine learning. They have been used since 94, 95, in the early 90s. They were introduced by Lecan and others. And they are sort of in some ways state-of-the-art models in vision. Means these days vision transformers have taken that over, but there are lots and lots of convolution type models. Then the other thing is that convolutions, unlike Fourier transforms, are local, so one can efficiently use locality in some sense. And also there was a paper by Lars Rotuto and Eldad Haber where they link convolutions with CNNs with finite difference methods. And it's a very easy link that one can make. You can think about it during lunch break. How is a CNN linked with a finite difference method? But so since finite difference methods are quite successful for PDEs, it makes sense to think about it, right? But remember that if you take plain vanilla CNNs, these are not Renos, and this was the issue. So somehow we have to bring back this continuous discrete equivalence, this function space consistency, and one attempt that there are other choices that one can make. One attempt is, that's why I say convolutions strike back. I'm a big fan of Star Wars movies and the Star Wars series, so this is based on that. It's a bit of an evil connotation to it, Empire Strikes Back. But anyway, so now this was in this paper here, which is called Convolutional Neural Operators. And let me just finish in the last 10 minutes just giving you a very rough introduction to what it is, because details I don't have time for. So the idea is a little bit like FNO, right? So you start with a function, you're going to project it onto a latent space. You work with a series of layers, right? This is, after all, a concatenated composition. and then you project back into the output space that you want. So there are two key building blocks here. Means just like in CNNs, there are two key building blocks, or also in FNO there are two key building blocks: convolution, because there it was done in Fourier space, and nonlinearity. So this is going to be the case. But now our objective is to design this kind of a representation equivalent neural operator. So instead of using discrete convolutions, what we are going to do is that we have, first of all, our inputs are going to be band limited. So we know a priori that we take a function, we take a band limited function, so we can equivalently represent it on a grid. We know exactly that, right? Otherwise we are in trouble because we can have aliasing errors. So you have band limited functions, and then what are continuous convolutions? The details are in the paper, so you have band limited functions. We convolve them with a discrete kernel essentially. So you can interpret it using a Dirac distribution, and then this kind of a commutative diagram follows. Okay, so if someone is interested in the detail, please ask me during the break and I can explain it to you. So you have a discrete kernel, but you use a continuous evaluation or a continuous convolution, and because you are dealing with band limited functions, you have this kind of commutative diagram. So this bit is going to be a Reno. And the main sort of innovation comes from how to use nonlinearities, because remember that nonlinearities, when we applied them, they are breaking these band limits. So the way is, it's actually inspired by some architectures from vision, from image generation, StyleGAN 3. So the idea is that just for the nonlinearity, what you do is that actually it's shown here, that just imagine that you have like a square type nonlinearity. So you know that 20 signs, they go up to 40 signs. So in order to keep this band, we ourselves artificially increase the signal to 40 signs, let it have 40 signs, and then go back, right? So this is done by using what are called upsampling and downsampling operations. So first we take our signal, you embed it essentially by zero padding into a signal with more frequencies, potentially much more frequencies. You apply the nonlinearity, expecting that the nonlinearity stays within the band limits, and then you project it back. So these are the shown graphically here. You start with a signal, you increase the resolution, apply the nonlinearity, and then you decrease the resolution, and you keep it in sort of, and this also is a commutative diagram under certain conditions always, and then we can show that this is a Reno. So this is a way. So the two building blocks are you modify convolutions and you modify nonlinearities, so that these are representation equivalents. So this is a way to fix CNNs to resolve our problem. But in practice, of course, our actual architecture, this is some cartoon of what goes on, but in practice we have, why is this not, yeah, in practice we have a much more richer architecture. So this is how it looks like. As you can see in practice, so let me explain it in 5 minutes and then we probably stop. So you start with the signal, U here, which is now taken into a latent space by this projection operator, which is also there in FNO, for instance. And then you apply different operations. For instance, you can upsample, you can use, these are the different operations. So you can use a convolution here. You reduce the resolution but increase the number of channels. This is very standard in convolutional architectures, because the idea is that you extract low frequencies first, and then, or you separate the frequencies, you separate the scales, and then you keep on using this sort of convolutions and nonlinearities to extract even more sort of low frequency features, and then you use some residual connections and you build it up, and you do the same. You have some skipped connections here. And this is a bit of engineering, of course, because you want to have a multi-scale information processing. You want to separate your signal into different scales, and you want to combine them in a nonlinear manner. And this is roughly the idea. And you do so because each of these building blocks is a Reno, the way we put them together, the whole thing is going to be a Reno. So this is sort of the, let's say, the principle behind CNO, or a convolutional neural operator. And it has the right kind of properties, more or less by construction, because for instance, it is a Reno, so it is a representation equivalent neural operator, because we had built it up using these sort of modulated nonlinearities and modulated convolutions. By the way, this is, you can think of it as a UNet or an operator unit, because it has this It has this sort of U-type structure, but there are some additional details that we introduced into this entire architecture. So it is a Reno by construction, and as I said, means almost anything reasonable has universal approximation theorems. So it can, as long as it can be done for measurable operators. But if your operator, for instance, is continuous and it has a modulus of continuity, it maps a Sobolev space to another Sobolev space, then essentially by approximating your inputs and outputs with band limited functions, you could prove that you have this kind of universal approximation. And of course, there are some implementation details that are out there in the code. So it also has the same sort of properties that FNO has. We are almost done. FNO has and DeepONet has. In addition, by construction, it is a Reno. So this is sort of the main advantage. And after the break, we will see whether this works in practice or not. Right? Since I'm presenting, it probably does, but we will see that. Okay, so with that, I will be happy to take some questions about DeepONet, FNO, and a very, very quick introduction to CNO, but otherwise we go for lunch. So, questions?
The questions? Oh, there is
yeah.
One.
Yes. I'm having a hard time reconciling the theory here and in practice the fact that sure when you have a continuous function you need a discrete representation and then you can do your neural networks, but in practice you don't have a continuous function as an input. You have an evaluation, a sample, a vector of points corresponding to that function.
Yeah.
And that sample usually has nothing to do with the discrete representation you chose in your scheme, right? So how do you go from the initial discrete representation to the discrete representation that you need? And do you need to sample specifically according to the discrete representation you want?
It's a very, very good question. So for instance, let's look at band limited functions. This is sort of the setup that we are in. Let us look at band limited functions. And let's say that you are given an input signal, which is if things are below the Nyquist barrier, you can do nothing anyway. So this is a big caveat here, right? You have to have enough resolution. But if they are above the Nyquist barrier, for instance, then you can always go between one and the other. Because if you're given a function, let's say, which is on a, because remember that I had this change of frames formula, so change of basis formula. So I can always go between different discrete representations. And so you get whatever in practice. If it is below Nyquist, this theory breaks down. But above the barrier, then what you do is that you just resample it to the grid that you have, the computational. So you have a fixed computational grid. So just like in FNO, you have a fixed Fourier grid in some sense because you're projecting onto Fourier modes. Here you do the same. You have a fixed grid to which you have to reproject. But this is just essentially a upsampling or a downsampling operation. And this is linear, very quick. So indeed there is an issue, but you have to because your kernel fixes that in some sense, right? And you can always change between different bases or different frames. So this is what is done in practice.
And if you have the choice of sampling, like you actually have, let's say, an analytical function as an input, so you can choose the vector of representation you want. Should you sample differently if you do FNO or CNO or?
Should we sample differently? I have to think a little bit. What advantages will that accrue? By the way, there are some limitations that I'm going to discuss of all these methods, particularly with complex geometries. But there is no I think this should be done based on computational purposes, right? So, yeah, do you guys have a better answer than I have, or
for the points?
Yeah.
For FNO, you can only sample.
Yeah, FNO. Yeah, this I told that I will tell them, right, that with the uniform grids. Sometimes, you know, they know more than me, so.
Actually, from the implementation perspective, you can only use grid points for FNO.
Yeah.
Because in practice, use the FFT algorithm inside, and so there is no chance unless you implement the Fourier transform like in the integral form.
Okay, so.
Thank you. Okay.
There is one more question.
One more question, but there is also a question online.
Yeah, it's fine. Actually, I was just going to ask if you could use like new FFT, like non-uniform, then you could actually choose how to sample.
This is, but then of course the nice sort of log linear complexity will be gone. So this is this is always a payoff. There's a question on the chat.
One question: is it possible that being a Reno can also depend on the optimizer?
No,
and
because
not only on the architecture. So answer is no.
But this is a good. There is a, maybe the question is more complicated than how it is sounded, right? So there are some bits here that are important. So Reno is a property of the model, and potentially of something of the continuous operator, right? Because you also, so just imagine that you have a learning process where all your samples themselves, your training samples are aliased. Then there will be aliasing errors contained there. I presume that the question is asking about, is a question like that. So indeed, you have to ensure that when you train, you don't have aliasing errors. Means, for instance, if you...
It was not exactly errors, it was... because when you improve the resolution, we may get the loss harder to train, perhaps. Okay,
perhaps this is Okay. It does not say anything about the training process because it's a property of the model and of the operator. So the training process could, of course, this could change. And
other question about the lifting phase and how do you think the choice of the high dimensional space impact the training? So the second question about the training. People are anxious about it.
People are always anxious about training. That's why they should do the exercises in the tutorial today, because this will precisely deal with this issue of how, maybe Roberto can. I will tell an answer afterwards, but...
I mean, in the tutorial we're going to fix one high dimensional value. But usually it's always like a matter of depends on the problems, and most of the time you end up doing hyperparameter selection on this variable.
Yeah. So in general, the choice of the latent space is difficult to understand theoretically. This is all that I can say. Means, it has to be high, but how high, I don't know. Means usually in my experience, it is significantly larger than so let's say Navier-Stokes, you have 2 or 3 velocity components, and let's say pressure also you're training, so 4 components, but you would project it to like 64 components. There is in the paper that we wrote on FNO, there are some bounds or some theoretical motivation of this choice, but that's the only one that we have seen where the theory really matters. Elsewhere it's always a question of practice.
Okay, I have a short question. So for solving PDs, there might be problems with the boundary condition. Okay,
absolutely.
So where are boundary conditions in all this picture you gave?
This is a very, very good question. This will be discussed quite a bit after the break.
Okay.
But for instance, you already saw that I was using FFT and so on and so forth. So what kind of boundary conditions can you deal with? So boundary conditions, indeed, general boundary conditions are an issue. With CNO, there is no reason. Means you can, or DeepONet certainly is very, very general. So FNO, on the other hand, has some issues with boundary conditions. So boundary conditions are, and complex geometries, but I'm going to talk about them at some length afterwards.
Okay, thank you. Okay, so we thank you for the lectures this morning.
And you have some announcements?